Hi, everyone. Thanks for coming out to the first theory seminar of the semester. Normally, this is going to be on Wednesday in Lubrano, like there, but today it's Friday and we're in here. So I'm very excited to introduce Karthik C.S. Karthik is an assistant professor at Rutgers. He completed his PhD at Weizmann and then did postdocs at Tel Aviv and also NYU with Subhash Kot. He has received many awards, including an NSF career. How did I do? Is that?
That's perfect.
Oh, he's also a stand-up comedian. So if you don't enjoy his talk, it's your fault. And with that, I'll let Karthik just get into it.
Thank you. Yeah, thank you for the invite. Yeah, I'll try to tell some proofs, and if you don't agree with them, they're jokes. So this is a collection of works, and I've tried to summarize sort of this recent progress in this area in the intersection of theory of clustering and hardness of approximation. So I'm going to try to motivate this. So here are a bunch of images of handwritten digits, right? Clearly, we all agree that there are 10 digits here, and so there are 10 clusters, and the goal is to sort of group them based on what digit they're trying to represent. And each image itself, you can think of it as some grayscale image. So it's some 28 cross 28 dimension pixels. Each entry is between 0 and 255. So it's some high dimensional vector. And you can, in some metric space, model it as I want all the vectors close by to correspond to the same digit. And then you want to cluster these points. So in abstraction, you have a bunch of points in space. And you want to group them based on some notion of similarity. And this task is called clustering. It's the task of classifying input data. And this appears everywhere. For instance, you want to cluster because when you cluster things, the things that are in common reveal something about functionality, like in a gene expression. Or sometimes clustering itself is the end goal, because you want to partition the data so you can do targeted advertising for each part. Or you want to just, you're running a newspaper agency and each data point is an article, and you want to prepare like some K representative articles of the publication. And so you want to cluster them and pick one representative from each cluster. Or data exploration. You just cluster them to figure out patterns and learn underlying metric structure and so on. Good. So let's model it mathematically. You have gamma and delta. Gamma is some set. Delta is some distance function. It's a metric space. And now you are given as input some point set x and the number of clusters k. Okay. And what is a clustering of x into k parts? Well, we can think of it as a pair, C and sigma. C is your set of centers. It's k centers. And sigma maps every point in x to one of the k centers. So in other words, it partitions x based on which of the k centers it maps to. And what do we want in the end? We want sigma to be good. Good is a very subjective thing, but it can be formalized. So this is roughly what like a clustering problem would look like, at least center based. And this is what is called the continuous version. Because you could pick your k centers from anywhere in the metric space. Sometimes there is the discrete version where you are given as part of the input another set of candidate centers, and you must pick your k centers from this set of candidate centers. So there's this distinction between discrete and continuous, and in some applications you would want the continuous version. Like for instance, in a computational geometry setting, you would want to be able to pick centers wherever. Whereas if you're trying to data summarize, you want your center to be a data point sometimes. So the discrete version makes sense. So it's interesting to study both of them. And this notion of sigma being good, it's studied under various objectives, like k means, k median, k center, min sum, correlation clustering, and so on. But we'll fix two things which we are going to study today, like look at k median. In k median, you want to minimize the sum of distance to the map center. Right? So for every point, you look at the distance it takes to go to the center it's mapped to, and you sum and you try to minimize this. And in k-means, it's the distance square. So this is the two things. In the distance, typically we think of LP metrics. Any questions so far? So this is the, so far we have just talked of the mathematical modeling. You can ask a computational question for it, which is given, say, in the discrete setting x, s, and k. X is the points to cluster, s is the set of candidate centers, k is the number of clusters. Find me a classification. Okay, and you can even ask approximately minimizing, right? Like we are okay with some loss in accuracy. And when you think of hardness, we study what are called decision problems. So it would be something to this case. You want to distinguish if the given input falls in which of the two cases. In the yes case, there is a classification such that the total cost is at most beta. And in the no case, for every classification, the cost is at least 1 plus delta times beta. So this, if an algorithm can solve this efficiently, then we say we have an efficient 1 plus delta approximation. And if you want to prove hardness, you want to prove it for the largest possible delta. What do we know about this problem? Well, it's NP hard when k is 2 or we are in the Euclidean plane. So when the dimension is 2, it's NP hard. But when k is 2, it's also NP hard. And if both of them are fixed, then it's in polynomial time. Now you can ask, what about polynomial time approximation schemes? So approximating it to any 1 plus epsilon factor. This is when k is fixed or d is fixed, this exists. So we're now interested in the case when both k and d are a bit large. So this is what we know. So this table, I'm looking at 4 metrics which are of interest, which is general metric, where you are just given all pairwise distances which satisfy triangle inequality, and then 3 geometric metric spaces, L infinity, L1, and L2, which are like the 3 most popular LP metrics. And then there's the distinction between discrete and continuous, k-means and k-median. This is what this table roughly captures. It doesn't make sense to ask continuous in the general sense because you're just giving every pair. It's a discrete metric by definition. But continuous can be asked for all LP metrics. Now, this table used to look much more interesting last year because every single column was filled by a specific paper. But this specific year we have these 2 really big results which sort of just clean up the whole thing. So everything related to k-means comes from this first paper, I think in Fox 25, and everything related to k-median comes from the Stock 25 paper. So that's it. So the state of the art is this. You can see that the numbers look roughly like 5 something for k-means and 2 something for k-median. Yes.
So this now?
Yes. Right. 2 times the opt. Yeah. Yes. These are approximation algorithms in polynomial time, right? But also the thing I want to really say is that the fact that there are so many papers published means that it's of active interest to the approximation algorithms community. So in order for them to obtain optimal results, one needs to know what the lower bounds are or the hardness factors are.
So this assumption on k.
Yes. Yeah. Any KD, general thing. Yes. You might also see that in L infinity, there is some distinction, like the continuous seems harder. But L1 and L2, there are core sets, so you can show that continuous can be reduced to discrete. So the lower, like whatever you get for discrete also applies for continuous. Okay. Good. So this is of active interest. Now let's talk about the hardness of approximation up till 2019. In the general metric, we had really nice numbers stating all the way from 99. So these are reductions based on set cover type things. Because you can just put what the distances are, you can just get the right kind of things. I do believe these are the right answers because in FPT time we can achieve these factors. So it's just about transferring this FPT technology to polynomial time technology. And people have been doing that. So the papers you saw use that kind of ideas. So I do believe these numbers are right. And these are not some weird numbers. 3.94 is actually 1 plus 8 over E. It comes up from the greedy algorithm for set cover max version, which is 1 minus 1 over E. We will see these things a bit more. And that is 1 plus 2 over E. Good. So for general metric, I believe from the hardness, there's nothing much to say. But then you can ask about LP metrics. So let's say L2 and L1. There are these papers from 2000, which give something very, very small, like less than 1.01, much less than 1.01. For L infinity, again, something very small again. Like, and it's not like people haven't tried. Like people are trying. And then the continuous version. So these are all discrete. 1.0013, like something very small. Good. And I do believe it's not because they didn't have the technical thing. It's more like you need the right conceptual approach to the whole thing. And so I'm going to show some proof sketches today, and you'll sort of get convinced that the proofs are right. So it's mostly about like looking at it from the right way, where the proof just sort of automatically follows. So before I do this, I want to sketch why is the difficulty of transferring this general metric to LP metrics happening. So I want to show the proof of the general metric hardness. Okay, so we start from the max coverage problem, where you are given a universe and a collection of subsets, and you want to find k subsets that cover as much of the universe as possible. So you want to find k subsets that cover the max fraction. So for this, this is an NP-hard problem, and there is a greedy algorithm to approximate it, which is at every iteration you pick the set which covers the maximum number of uncovered universe elements. And you keep doing this k times, and you can show that it achieves 1 minus 1 over E. And this is in fact tight. So Feige had showed that to distinguish the case where there are k sets that cover the entire universe versus every k sets cover at most 1 minus 1 over E plus epsilon fraction of the universe is NP-hard. So we have a tight understanding of this problem. Ta-da. Yeah. So we're going to reduce from this. And the intuition is every universe becomes a point to cluster, and every set becomes one of the candidate centers. Okay. So from this, we are able to build an instance of k-means, let's say, where x is the points to cluster. Nice. I think I might know why. Let's figure it out if that is true. X is the points to cluster, and that's equivalent to the universe. S is the set of sets like that we have, and that's the set of candidate centers here. So in the S case, there is some classification such that the cost is exactly the number of points to cluster. So it's 1 per the number of point. And in the no case, it's 1 plus 8 over E times the number of points. Let's see the proof. So you are given a set system. So the thing in red are the sets, and the thing in green are the universe elements. Well, the thing in green we can think of as the points to cluster. And the thing in red are the centers, candidate centers. And we need to now specify the distances between them in order to. So if a set covers a universe element, put it at distance 1. Otherwise, put it at distance 3. This satisfies triangle inequality. Right? So in the S case, there are k sets that cover all of the universe. So those k sets correspond to k centers. And so for every universe element, there is one of your k centers at distance 1. So the distance, the total cost of the k-means objective is going to be the number of points.
So what you're saying is like
right. So I would have ideally wanted to place, say, some large number instead of 3, if the set doesn't. But then there can always be a 3-step walk. And so 3 is the maximum I can allow. So in the yes case, we are done. In the no case, pick any k centers. This corresponds to k sets. That covers 1 minus 1 over E fraction at distance 1. And for the remaining 1 over E, you are at distance 3 from the k centers. But then since we are talking of distance square, it's 9. So it's 1 minus 1 over E plus 9 over E, which gives you 1 plus 8 over E. So that's how that number comes up. And of course, the issue is, why do we have the situation where we have these nice numbers here and here? You want to, in this case, realize these points that we constructed as points in this metric space. And when you try to embed this point set that you constructed, you will incur a lot of distortion. And the distortion just kills all the gap, 1 versus 3 that you had. And these results are actually obtained by making sure that the point sets have bounded VC dimension, and you can compress this thing so that the distortion is at most some 1 plus delta. So fine, when you embed 1 becomes 1, 3 becomes some 1 plus epsilon, so you get some 1 plus epsilon gap. And so the real insight what we need is we need point sets which embed well, and at the same time as hard as the original things that we had. Okay. Good. Now, in a series of papers, like all of this together is some journal submission that has been promised to be written. Yeah, because there are many things from here and there that we have to take, but I'm hopefully trying to put everything together in the talk. And this talk motivates me to write the journal thing. But with Vincent and Eung, we sort of now have state-of-the-art results for everything. So I want to present it in a table. So for the discrete, we put forth this hypothesis called Johnson coverage hypothesis, which I'm going to say what it is. But assuming that, what we can say is something quite surprising, that L1 metric, despite all its geometric structures, doesn't give you any advantage over the general metric. So you can obtain the same factors for L1 as you did for general. So the geometry didn't really help. And L infinity, we can obtain it even unconditionally under NP hardness. So we don't even need a hypothesis. So we can get the same as general metric for L infinity. And L2, we can get some improved bounds, which are still nice, much larger than 1.001. So this is what we get for these things. And I need to make the point that these are all in log n dimensions. And log n dimensions is tight, because if you go below log n, you have sub-exponential time algorithms. So that would contradict ETH. So this is the right, so it's even tight in terms of dependency on dimension. And for continuous, there is a slight strengthening of JCH, which is just that it's dense. And we can, for instance, in L infinity, we get surprisingly 4 and 2, which is much more than in the general metric. Okay, so this, if you're an algorithm designer, this should be surprising, because if I tell you that you're allowed to put k centers anywhere in space, that's more flexibility, as opposed to saying it should be from a set of candidate things. There's no combinatorial constraint. But somehow in L infinity, this actually becomes a curse, because finding the right one takes much more time. We'll actually see this proof as well. But yeah, so you get some nice numbers here as well. And the point I wanted to say is these things in red that are there, I believe are tight. So any improvement needed should be an algorithm question. So there is no hardness question there. The things in black, fine. I think there is scope from both sides to do things. But for the things in red, I'm done. It's up to you guys. But then the
point set is too large.
Yeah, if you go
The dimensions that you're working in.
right. So for instance, these L infinity bounds are in n dimensions.
Yeah. Oh.
And so I think for log n dimensions, you can always say continuous is at most as hard as discrete, because you can do these kinds of arguments. So given that this is already done, so the sort of open questions are how to make progress on this hypothesis, which I haven't told what it is, but and then how to obtain optimal factors, because this doesn't seem optimal as I've marked. They're still strong, but not optimal. And the nice thing is all of this work sort of builds some kind of uniform framework. And there's sort of a lot of interconnections between the things. So it feels like you're building a theory for this whole thing. Okay, good. So let me just focus on the discrete version. Nice.
Monitor is always works.
Okay.
Projector is some problem.
Yeah, when I try to be the center of focus, it just disappears. So this is the set system we had, right? Like from max coverage. So the Johnson coverage hypothesis just says the following: that this, if you think of it as a graph, a bipartite graph, if this graph can be embedded in what is called the Johnson graph, which I'm going to talk about, then the problem remains still hard to approximate to 1 minus 1 over E factor. This is what, at a high level, like this is the informal version of it, says, is that take these set systems that we had, and if they are realizable as subgraphs of what is called the Johnson graph, then it's still hard to approximate to the same factor. Okay. So I'm going to try to make this more precise by introducing what is called the Johnson coverage problem. Your input is, you have a universe of size n, and your input is collection of t size sets of this. Okay, so you have some t size sets, and your goal is to find t minus 1 size sets. Right? Every t minus 1 size set can either be completely contained or not. So when it contains it, we say it hits it. A t minus 1 set, when it's contained in a t set, we say it hits that t set. And now in the yes case, there are k many t minus 1 sets that hit every one of those input t sets. And in the no case, any choice of k t minus 1 sets is going to hit at most alpha fraction of the input t sets. Okay. Yes. Right. So if how does this connect to max coverage? I'll say it later. But if instead of t minus 1 we asked for 1, so find the universe elements that hit all the t sets, that's essentially max coverage. Because you think of the universe elements are your sets, and these are like, every universe element, you look at which sets am I contained in, like a hitting set version, and then you get these t sets, which is the number of sets a universe element is contained in, and this gives you a max coverage version. Now this is the hypothesis that as we increase t, then the inapproximability approaches 1 minus 1 over E. So this is the hypothesis. No, because SCTH has something about runtime, right? Right. So this has nothing about runtime. Right. This is precisely like Feige's result, if you the max coverage version, also says something similar to this in spirit. It says that as the size of the sets grows, the inapproximability factor approaches 1 minus 1 over E. But there it's t versus 1. Here it's t versus t minus 1. So it's analogous to Feige's thing. It's like a strengthening. Set is more about runtime, so we are not talking about that. Because Feige's result is for when it says about having 1 sets. So we want t minus 1 sets. So there is a distinction, but maybe I'll explain a bit more now. Next slide. So think of t equal to 2. So I claim this is just the max version of vertex cover, because you're given a graph, you want to find k vertices that cover as many edges as possible. Now think of your vertices as your universe, and then your edges are sets of size 2, right? So if t equal to 2, now just go back and interpret this. You are given a collection of edges, and you want to find t minus 1 is just 1 now. So you want to find k vertices that cover everything versus k vertices cover only an alpha fraction. You want to distinguish between the two. So this is just the max version of vertex cover. And for this, we know, like from under unique games, that the 0.944 in approximability. Okay, so there's already some weak version we can tell from unique games. And now, if instead of picking t minus 1 sets, we ask about 1 sets, like sets of size 1, then this is exactly the max coverage problem. So, and as t approaches, increases, this gap approaches 1 minus 1 over e. So the question is now asking the same thing, but instead of 1 sets for t minus 1 sets. Okay. Looks simple enough, but now we'll start getting into very hard combinatorial questions. So if you want to analyze the LP integrality gap, you get this kind of a nice question. The smallest collection of t minus 1 sets that hits all t sets. Okay. This is a nice natural combinatorial question. For any n and t, what is the smallest collection of t minus, and it should be in extremal combinatorics. Turns out it's open from the 1940s. This is the hypergraph Turan number. And we have really no idea how to do anything here. So without answering these kinds of things, you can't just go on with trying to transfer the LP integrality gap into a hardness result and things like that. Okay. And this question itself was recently resolved for t equal to 3 in 2016. Yeah, it's an annals of math paper. Everything is just way too hard if we just go head on. Nevertheless, using this, we can get some improved SDP gaps for the clustering things. We can still use the t equal to 3 paper in a black box way to do something. Okay. So what can we show for this hypothesis? Well, for t equal to 2, we know 0.944. And we can also show the following, that if you are given sets of size 3 and you want to find sets of size 1 to hit them, then we can get a 7 over 8 hardness approximation that's under NP hardness. So it's free of any assumption. And this is already useful to get all the NP hardness factors I listed. I mean, you can say something, but then it doesn't give you anything for the embedding.
But is that hard?
Yeah, you can sort of tweak max coverage and get that.
Okay.
So, for instance, t and t over 2, that's a natural thing. But that you can just, by subsampling, reduce to vertex coverage. So that's not the right question to ask. So you really want t and t minus 1. Yeah. Okay. So yeah, you want them to be as close as possible, and you'll probably see this why that's needed. Okay. So just to give a high level of how the discrete things are proved, so you have 3 ingredients. You have this instance which is hard with all this structure. And then there are these tools which are dimensionality reduction tools which only work for these instances. So LP metrics generally don't have dimensionality reduction. It's only L2 that has. But for these specific point sets, we can do it for all LP. And you can bring it down to log n. And this comes out of a communication game as the transcript of some communication game. And then finally, you want to combine this and embed it into LP metrics some way. And that's how these proofs roughly look. So if I have time, I'll show these details at the end of the talk. Okay. But the point is, it implies these kinds of things. So it implies all these discrete things. Just JCH star just says that the number of input sets is large. It's not a sparse instance. And you get these kinds of numbers as well. But then to get L infinity, these things, we need a different approach. And I want to tell this different approach. There's a nice new graph problem. And I want to connect it eventually to JCH, so that it's all in one framework. Okay. So now, forget about what I just said. There's a new graph problem. We call it K min-max matching. So it's a matching problem. A priori, it shouldn't be clear why matching has anything to do with clustering. They don't seem like the same kind of things, but we will connect them. So you're given a graph G, and you're given K, and your objective is to partition the vertex set into K parts, such that when I look at the induced subgraph, in each part, I want to compute its max matching. And then I want to minimize the sum of the number of edges across the parts. So it's min-max matching. It's a simple enough problem to state, and I want to claim that this lies at the heart of continuous clustering. Good. So is the problem clear?
It's a general graph.
General graph, yeah. Any graph and things like this. Okay. So now I'll show a proof where I'll connect it to clustering, giving you the 4, let's say, and 2 for k-median and k-means. So you start from an instance of k-min-max matching. You're given a graph G, and you are going to output a k-means or k-median instance where every vertex is going to be a point. The number of coordinates is going to be the number of edges. And we are in the L infinity metric. So you're going to take the max difference across the coordinates. So suppose there was somehow this k partition of the vertex set such that the sum of the max matching across the parts is at most delta times v. Then we'll show that the k-means cost is 1/4 plus some order delta, and the k-median cost is 1/2 plus order delta. It's instructive to think of delta as 0 or approaching 0. So really what it says is that if you can partition the vertex set into k parts such that they're all independent sets, right? It's k colorable. Then the k-means cost is 1/4 and k-median cost is 1/2. On the other hand, if for every partitioning of the k vertex set, we know that the min-max cost is at least alpha, then you will get that it's at least a 1/4 plus 3 alpha over 2 and 1/2 plus alpha. So think of alpha as some substantial constant. Then this separates them by that amount, up to 3/2 and 1 factor. So we'll see this proof. So you are given a graph G, right? So you orient the edges arbitrarily. Now for every vertex, we want to build a point. Let PV be that point. And now every coordinate corresponds to an edge. This edge is either incident on the vertex, or not incident on it. And since we have oriented it, it's either incoming, outgoing, or not adjacent. So if it's outgoing, write +1. If it's incoming, write -1, and otherwise write 0. Okay, so this is the construction. Now let's make some simple observations. Suppose 2 vertices are adjacent, right? So they have an edge. Then on the eth coordinate in which they are adjacent, one of them will write +1, the other will write -1. So their L infinity distance is 2. And if 2 vertices are not adjacent, then on every coordinate, only one of them will write a non-zero entry. So their distance is 1. Okay. Good. Now this is a bit more interesting. If you have an independent set, and you look at it as a set of points, there is a center at distance 1/2. Why? Every pair of them, only one of them writes a non-zero thing. So for the whole points, no 2 points will write on any coordinate non-zero, because that means they have an edge. Since it's an independent set, for every coordinate, at most one of them will write a non-zero thing. So let's say one of them writes 1. Then you pick the center to have 1/2 on that coordinate. So your centers will all look like plus or minus 1/2 in entries, and the sign is depending on which vertex writes a non-zero thing there and what is its sign. So you have a center at distance 1/2. Now here is some claim. You take a subset of vertices S such that the max matching induced to that subset is at most beta times, the cost is beta times S. Okay. Here is something about the one median, like a lower and upper bound. Yes. So take any 2 vertices and fix a coordinate. Okay. Now that means that if both of them have an edge, that specific edge, because every coordinate is in correspondence with an edge, then but it's not adjacent. Then it's adjacent, right?
But yeah, but in the case where they're
Non-adjacent. So one of them will write a 0. The other will write +1 or -1.
why?
No. So take the 2 points
Yeah.
and look at a specific coordinate.
Yeah.
Okay. So this corresponds to an edge.
Yeah.
Okay. Now that specific edge cannot be incident on both of them.
Yeah.
It can be incident on one of them or none of them.
Yeah.
If it's incident on none of them, both of them would write 0.
Yeah. Which would make.
Asking a corner case, maybe there's no edge going.
If a vertex is isolated, then the corresponding point is all zeros. And you're saying if there are 2 points that are all zeros,
That's what he's asking.
I'm just making sure that I'm understanding the definition.
yeah. Just it's connected. Okay. I don't even think of the corner case.
Yeah, I just wanted to make sure I understood what was going on.
Okay.
It's not a meaningful question.
Yes.
Sorry, I think I zoned out.
E dimension.
E dimension.
And the number of points is the number of vertices. So I want to convince you of, say, the lower bound, and then the upper bound sort of automatically follows. So let's look at the lower bound. And again, we are trying to compute the median of S. Right? The median is the center at distance half, because S is some independent set. Okay. So let's say the center is CS, and you take some point V, like vertex V in S. Okay. And now we are just summing over the distances. That's the cost of the median.
Sorry, can you go back just a little? I didn't read anything. So S is
So for every subset S,
that's
some constant. No, I don't. I want to analyze it in both cases. So
okay.
it can be 0, but it can also be like half.
Right, but you're taking the equal sign.
Yeah. So it's for some beta, and I'll analyze it using some bounds. And the point is, this one median that is there. My idea would be look at everything not in the matching. That forms an independent set.
One median PS is the objective function for choosing set in the out.
That minimizes the sum of distances. Yes.
Okay.
But in the L infinity. So, yeah. And the high level idea is I would look at this set S, remove everything not in the matching, like that part that's not in the matching forms an independent set. This independent set we naturally associated with the center at distance half. Fine, I'll just pay that half, and then for the rest I'll pay whatever I have to pay. So that's what I'll try to do here. So look at all the things in the matching. So I collect them. So I write them as the pair, and we wait. I'm not touching anything. So this is, I just collected every pair that forms in the matching, and then everything else not in the matching. Nice. Yeah, no, it's fine. And then this, we use triangle inequality to lower bound it. So this plus this might as well get rid of the CS. Instead of going through CS, we directly go to there. So this is at least the distance directly. Plus, for this, we know we have a center at distance half. Okay, so that's 1 minus 2 beta. And then when you, and this, when you look at the distance, you are writing 2 plus 1 and minus 1. It's at most 2. So you get 2 beta S plus this. So that's how you get the lower bound. And for the upper bound, same thing for this part. But here, we don't know what it is, but we know the center is like, plus half and minus half. So if one of them pays 3 half, the other pays half. So with that balancing, you get 3. So because 3 half plus 3 half is 3. So you pay some default. The whole point is, here's 2 beta S, there is 3 beta S.
I guess the point is you are
Right.
outside, you just give some.
I just give away and I don't care. In the yes case. In the no case, if beta will be very large, and I can at least bound it by some function of this thing. Yeah. And same thing happens for k-means. Instead of 3, you will get 9 half, because it's 3 half square plus 3 half square, which is 9/4 plus 9/4, which is 9/2. Okay, and now there is this result by the 2-to-2 games, which says that even for k equal to 4, in the S case you can partition it into almost a quarter-sized sets, independent sets, and in the no case there is no independent set of size epsilon times v. And this immediately implies for our min-max matching problem that in the S case, I can take 1 minus epsilon things, that forms an independent set, because if you partition it into 4 parts, so only an epsilon fraction can contribute to a matching. So it's almost 4 colorable. Or in the no case, you pay almost everything. Like however you partition it into 4 parts, you have large matchings in each of them. Okay, and then this gives you the 4 minus epsilon, the lower bounds that we want. In the S case, you have a cost n, and in the no case, it's 4 times n. Okay, so is this fine? And then you can sort of abstract it. This is for L infinity. If you want to do it for any LP metric, you want the adjacent things to be at distance at least rho, and the things that are non-adjacent to be distance 1, and every independent set to have a nice center at distance c. Good. Then if you run through the whole thing, you get something like, if this was delta, then this is 1 plus order delta, and if this is at least alpha, then it's some expression in terms of alpha and rho. Rho is the distance of the pairs that are adjacent, and alpha is coming from the hardness of this. So it's combining the metric distortion plus the hardness coming inherently from these things. Okay. Now I'm lying a lot here, because it's not this clean. There are more conditions, but this is morally what's happening. Okay. And then you can plug in, right? Like you can take the vertex coverage thing, and you can look at Euclidean metric. And in Euclidean metric, you can have it such that every pair is at distance 1, that non-adjacent, and everything that's adjacent is at distance √2, and the center is at 1/√2 from the points. And this is true for 0 versus 0.028. You plug it in, and you get that, assuming UGC in Euclidean metric, the cost is less than n versus 1.056n. You get some numbers based on this framework. And you can do, how do you go from this vertex cover to this min-max matching? Okay, let me try saying this. You take the vertex cover problem, okay? Then you look at the line graph. So every edge becomes a vertex. Now the goal is no longer to find k vertices to partition the edges. It's like now partition the vertex set into k cliques. Because if it forms a clique, it means there's a vertex covering all those edges. Then you take its complement. So now you have k independent sets. So that's how this is interconnected to vertex cover. And remember that vertex cover was generalized, you get Johnson coverage. So that's how the whole connection works. So yeah. Now, so vertex coverage, you can connect it to k min max matching. And the embedding that I was telling was just for every edge, you look at EI plus EJ or EU1 plus EU2 and normalize it by √2. So if 2 edges had a common vertex, then there are 2 coordinates where they write 1/√2. So the distance is 1. Whereas if 2 edges didn't have a common vertex, then their distance is √2. And you can find a good center for these things, which is the common vertex that is there in these things. Okay, so that's how you get all these connections. And then connecting the dots, well, there is a discrete version of k min max matching that you can say it exactly max coverage, and that connects to the discrete results that we had. So just stating the problem here, your input would be some m subsets of V, and then your objective is to pick k of these subsets And now when you keep k of the subsets in that graph, you remove the edges in those case, each subset. So you're sort of poking holes in the graph. So you have the complete graph. Then, I don't know, the subset 1, 2, 3 is there. So you look at the triangle 1, 2, 3 and remove it. So this is sort of like picking the k centers equivalent. So you pick k centers and you make them holes. And now you are in that graph that you constructed, you want to partition it into k parts such that you minimize the max matching across the parts. And this is, you can show from directly follows from max coverage. S case, you can partition it into k independent sets. And in the no case, the cost has to be at least 1 over 2e. So you get many of the discrete results follows from this. Again, these are the numbers. Good. How much time do I have? 1? Okay.
Sometimes we get kicked out at 1.
Okay. Yeah, so maybe I'll speak for like 5 minutes on dimensionality reduction, because this is sort of independent, and it's like a tool which you can sort of take, and we use it in our reductions. So I want to show how all of these Johnson coverage and everything comes together. So you have the alpha T Johnson coverage. So you're on the T sets layer, and in the no case, you cover almost alpha fraction. And you're given as input, so we can prove this thing. We can construct points in 0, 1 in the Hamming metric, such that in the S case, the cost is some n prime, and in the no case, the sum of distance square, the cost is 1 plus 8 times 1 minus alpha, right? So if alpha was like 1 minus 1 over e, that gives you the 1 plus 8 over e. Okay, and we're in the Hamming metric, so it's 0, 1 entries in Hamming. Okay, so if this was 1 minus 1 over e, comma t, which is the conjecture, then you get 1 plus 8 over e. And these are things you can prove under unique games, which is 0.95 and 2, like t equal to 2. Then you get 1.40, which is still a nice number. How does this go? Well, we wait again. This is all possible t sets. I represent them as nodes. This is all possible t minus 1 sets. I represent them as nodes. And you put an edge if this t minus 1 set is completely contained in the t set. Okay. Now you can actually, these are universe of n, right? So you can think of them as points in 0, 1 to the n, and you have the characteristic vector associated to these t sets. So you write a 1 if that element is there in the set. Now you get this interesting thing that if there was an edge, well, this t minus 1 set and this t set overlap on t minus 1 coordinates. So the distance is 1. And if there is no edge, then the distance is at least 3. So we have a nice embedding. So now you can see Johnson coverage hypothesis says that the universe and sets embedding embeds into this as a subgraph. And so you have realized it in 0, 1 to the n already with the distances that we want, 1 and 3. The only problem with this is that it's in n dimensions. So if in n dimensions, already this from Johnson coverage gives a simple proof of the whole thing. So now we want to reduce the dimensions here. And this is done using a containment game. So we are drifting to communication complexity. You have Alice and Bob. And Alice has a t set, and Bob has a t minus 1 set. And the goal is Bob can communicate to Alice. There is public randomness, so they both can jointly toss a random coin, see its outcome, and so on. And the goal is to determine if Bob's input is contained in Alice's input. And there's a deterministic protocol, just send everything. And okay, you have completeness 1. If it's contained, you always say yes. If it's not, you always say no. But we can come up with a randomized protocol where you send just a constant number of bits, where constant depends on epsilon and t. And you get completeness 1 and soundness arbitrarily approaching 0. So you get almost the same as deterministic, just small epsilon error in the soundness. And this uses algebraic geometric codes, or let's say for any codes, you take an encoding. So Alice and Bob will pick and they'll write their vectors, which is n dimensional, then take an encoding, and then pick a random location. And now Bob sends the entry in that location. So this is like similar to the equality protocol that is there for randomized communication. And now the point is, Alice will check if that SI is there in this TI or not, right? Because for every, so if I have T sets, I have T messages, and each one I encode, and then I send whatever the encoding of the ith location of each of those things. And now if Alice has T plus 1, like, or one more thing, and now has one extra possibility. So Alice is checking if all my possibilities, contain the possibilities that Bob sent. But you do it for every coordinate, and you do it at random. So the message length is just T minus 1 log Q. So instead of sending log n, I'm sending log Q, like a hashed value. And then the soundness is this, the distance of the code. And if you use AG codes, you get the right soundness approaching 0. Okay, and then this protocol can be used for dimensionality reduction. So I'll skip how, because this will take a bit more time. But the point is, every vector, instead of writing in EI, I will try to write down what for every randomness I would have sent. And this more or less works, because for most randomness, the behavior is very similar to sending the whole thing. So we show that instead of writing it as EI, if you write it in the randomized sense, because you're communicating less, the amount of message length is small, and the randomness is just log n bits. So you get it down to log n dimensions. Then there is some analysis, but fine. Okay, so let me talk a bit about open problems. So yeah, the most obvious one is if the Johnson coverage hypothesis is true. So there is this nice recent line of work by Bangale, Minzer, and Cote on characterizing completely satisfiable CSPs, and they're building these heavy machineries. But yeah, somehow this thing even goes beyond those. So if it's true, it must be very hard to prove. That's what we can say right now. And so the other thing is, look at the embedding which I just said, where you have characteristic vectors, which has cardinality t here and t minus 1 here. If you think of them as in Euclidean, as points in 0, 1 to the d, then this distance is 1, but this is no longer 3. It's root 3. And this root 3, we don't want to incur this, because this is what makes the hardness of approximation factors weak. So the question is there a different embedding, or a more specialized embedding that sort of gives better factors? So clearly you can't do it generically, but maybe you can realize some additional structure to get better things. Yeah, and finally let me end with this problem which I didn't talk about, but I really, really like. So case center clustering, this is from the 88. Like, we have done so much and we can't answer this. There is a very simple greedy 2 approximation algorithm. Case center is you're given a bunch of points, even say in the Euclidean plane. You want to find k points or k centers such that you cover everyone with the equal radius balls. Okay, so it's instead of min sum, it's min max. And there is a very simple 2 approximation algorithm. The hardness doesn't involve any PCP theorem or anything. It's like 1.83 for continuous. You just embed vertex cover and you get something. And to close that gap is open for like 40 years now. Yeah, it's very simple. It's undergraduate level kind of. I can teach both in an undergrad class, like both the hardness and the approximation. And nothing, yeah, we know nothing more. Okay, so that's it. Yeah.
Sorry, so
This one or the previous one?
just
So there is an algorithm which achieves 2 approximation by just doing greedy And then the lower bound is like 1.83. So yeah, can you bridge this gap? Yeah. But I feel like this question, because you still have to embed in Euclidean, right, should shed insights to this question, because it also gives us what structures yield better. So yeah, just understanding this, because it's much simpler. If you want to play with coming up with the tight results in Euclidean, you should start from the simplest, which is this. Right. So if my message was log n bits, which is the naive way to communicate, then I have to go for exponential in whatever the message length is to enumerate all possible messages, right? Which would be n bits. Like, so I need n coordinates down, and that's your standard writing EI as the thing. Now instead the message length was some constant, right? So exponential in that constant is still constant, but then the randomness is just log n coordinates. So it's for every choice of random coordinate, for each choice of coordinate, I have constant number of bits I write. And there are log n things, so it's just log n. So that gives the distinction between the two. It's to reduce the message size, because you're blowing up exponentially in the message size.